Hello everybody, I hope you're all doing well. So for today's concept to talk, we're going to be looking at the static equilibrium position for vertical mass systems. Okay, so typically static equilibrium position, we call it as a SEP. Okay, so SEP is the static equilibrium position. Okay, and for horizontal masses, the static equilibrium position is when the springs are unstretched. Okay, so SEP for horizontal masses. Okay, this is typically when the spring is unstretched. Unstretched length. Now, let me consider the system that you're looking at here. So in this system, initially the spring is at the unstretched length L0. Okay, this is a spring of stiffness capital K. Okay, then here is what I do. I take a mass and then I come and attach it underneath this spring, okay, at the end of the spring. And because I'm taking a mass and attaching it underneath the spring, it is quite possible that the spring is going to be stretched and comes to a static equilibrium position where the restoring force of the spring is balanced by the weight of the mass that is attached to the spring. Okay, so here is the situation that I'm going to show you. I have this already drawn up earlier. Okay, so now I come and I attach a mass down here. Okay, so look at this. So let me complete this. I guess I want to draw a mass. That's easier to draw a mass that way, or I'm trying my best. Okay, that seems better. All right, so here is the mass, and this was initially okay. Then here is the spring and the mass combined together, the same spring of the same stiffness K that is situated here. Now what's going to happen is that because of the fact that the mass is attached to the spring is going to deflect by a very small amount, as you can see, and this deflection I'm going to call it as delta static. Okay, so delta static, I'm going to call it as the static deflection of the spring. Okay, and how do I find delta static? That's fairly straightforward. I can draw a free body diagram of the mass with the spring force and the weight of the mass acting on it. Okay, so this is a mass little m. If I draw a free body diagram, let's take this guy. Okay, so I'm going to copy this and I'm going to bring this down here. Okay, and what are the forces acting on it? The forces acting on it are the spring restoring force. Okay, the spring is going to try to pull the mass up because the mass is trying to travel down due to the force of gravity. So this is going to be m times g, and this is going to be the spring force, which is k times delta static, right? And at this position I'm saying that the system is at SEP at this particular position. Okay, so this is the SEP position where the spring and the mass are in static equilibrium. Okay, and let me just mark this way. So this is SEP, and if I look at static balance, then at SEP I can very well see that K times delta static is equal to m times g, right? This is because the system is in static equilibrium. This is not any difficult to understand. Okay, so this is the first equation that I'm going to be writing. Okay, so I'll call this as equation 1. Now, and in this situation, even if I had a damping element, which I'm not showing here, but even if I had a damping element at the static equilibrium position, the damping element is not going to show any restoring force because a damping element reacts only to a relative velocity. Okay, so that's something that you want to note here. So at SEP, if you had a damping element attached to the mass, there would be no restoring force from the damper. from the damper, because the damping element only reacts to a relative velocity between its ends. Okay, so this is the brief note that I want to make here. Okay, so once again, the basic story is I have this spring which is just sitting there. Then I take a mass and I attach it to the end of the spring. I don't apply any force on the mass. I just let the mass deflect statically due to its weight. Okay, so at the static equilibrium position, the spring mass, the spring force is balanced by the weight of the mass, and this is the equation that you end up with. And the note says that even if you had a damper, there would be no restoring force from the damper, because the damping element only exerts a restoring force in the presence of a relative velocity. Okay, all right. Now what I'm going to do further is that from the SEP, I'm going to deflect the mass by a distance x due to some applied force. Okay, so here is the situation that I'm going to show for you. First thing is let me draw it out. Okay, so I'm going to take all of this and copy it. I guess I don't need that in a sense. Okay, so I'm going to bring it here. So from the SEP, now I'm going to take the mass and then deflect it by a certain amount, which means that I'm going to take this creature here, okay, and redraw it, maybe stretch it a little more. Okay, so this is going to be deflected down by a certain amount from the SEP, and let's say that this is the way things are. Okay, okay, so now the spring is stretched by a certain amount. So from the SEP, the mass is displaced by, let's say, a displacement deflected by this amount x, or x of t. Okay, and there is an applied force acting, so this is the deflection of this end of the spring as well. This is the x of t, and there is a force that is acting on the mass. Let's call that force as f of t. Okay, now what's going to happen is that both the mass is going to be in dynamic motion, because it is deflected by an amount x of t due to the force that is a function of time, which means I have to draw both the free body and the kinetic diagram for the spring in that for the mass in that sense, and the free body diagram for the spring. Of course, one can draw the kinetic diagram for the spring, but it's considered to be massless, so it's not going to make a huge difference to our life. Okay, so in this problem, or in this situation, the mass is now deflected from SEP. Deflected from SEP due to an external force f of t. Okay, and since we have this external force, the system is going to be in a state of motion. Okay, then we can apply Newton's law and so on. And what I want to show is one more figure. Okay, this figure from before, I want to bring it down here. Okay, this was at static equilibrium. Okay, so that's the situation there. Now if I deflect it, I'm going to draw the free body and the kinetic diagrams right underneath and right next to the situation that is shown. Okay, so here is the case. I can draw the free body diagram of the spring and copy that and paste that down here. Okay, then I can draw the kinetic diagram of the mass. Okay, and a free body diagram of the mass. Okay, so in the kinetic diagram of the mass, I'm going to have the mass times the acceleration. So this is just going to be pointing downwards, because I'm assuming that at that instant in time the mass is moving down, and the coordinate sign that I'm using is, okay, here is the SEP, this is the origin. Okay, and then if the mass is moving down, it's going to be assigned a positive displacement. If the mass is moving up, it's going to be assigned a negative displacement. Okay, so this is going to be m times x double dot. Okay, and this is the typical sign convention that we have adopted in the past, where we say that okay, this is going to be x dot and x double dot taken to be positive if it is traveling this way. Okay, so this is x dot and x double dot taken this way. So this is the kinetic diagram. Okay, on the free body diagram, what are the things that I'll be having? I'll be having, first of all, the spring restoring force. If I look at the spring, the ends of the spring will be in this way. They will be pulled down, and there will be an equal and opposite force. So this is going to be Fs. Okay, there will be an equal and opposite force Fs here as well. Okay, and this force will also be Fs. And what is the total force Fs? The spring has already been deflected statically by delta static, which means that on top of this there is also going to be a displacement x of t. So f of s is going to be k times delta static plus x. And one more thing that I'm forgetting here before I forget it, there is also the weight of the block which is acting vertically down. Okay, so this is going to be mg. Okay, so this is the free body diagram of the mass. Okay, and this is the kinetic diagram of the mass. And as you know, we will just sum forces up in the vertical direction on the free body and the kinetic diagram to get the equation of motion. Okay, so forces on the free body diagram, I'm going to say forces pointing down are positive, and sum of forces on the kinetic diagram, forces pointing down treated as positive. Look at the free body and the kinetic diagram. Here is what I'm going to have. I'm going to have f of t plus mg minus k times delta static plus x. This is equal to mx double dot. Okay, and if this is the situation, I already know. Okay, so from SEP analysis, we know k times delta static is equal to mg. Okay, this is what we had written down as equation 1, if you recall from here. Okay, so this was equation 1, this was at the static equilibrium position. Okay, and this is the relationship that I'm making use of as the dynamic motion takes place due to the applied force. Okay, that's what we have here. So if I do the substitutions now, then here is what I end up getting. So f of t plus mg minus k times delta static, which is going to be minus mg minus kx is equal to mx double dot, which means that I can get rid of these terms. So this is gone and this is also gone, and if I rearrange the situation, then I get mx double dot plus kx is equal to f of t. Or if I write it in the following manner, I can write it in the standard form by dividing through by the stiffness k, and I will end up with m by k x double dot plus x is equal to f of t by k. M by k is nothing but 1 by omega n square. Okay, so this is 1 by omega n square times x double dot plus x is equal to f of t by k. Okay, where omega n square is equal to k by m, which is the natural frequency of the system. This is something that you have seen in the previous videos, okay, the previous lectures. Okay, so this is the standard form of the equation of motion. Okay, if you had a damping element, I would just have an extra term that is velocity dependent on this particular equation, but it's not going to change anything by a whole lot. Okay, so here is the basic summary of what we want to say. When a mass moves in a vertical direction, okay, so this is an important point. You see that this equation of motion does not contain the term mg. Okay, so notice does not contain the term mg, or the weight of the mass. So which implies that if a mass moves in a vertical direction, okay, so when a mass moves in a vertical direction, its weight can be ignored provided the deflection of the mass is measured from the SEP for a system containing a spring, containing elastic springs. Okay, so the basic story is, if I'm starting the problem from SEP, so this implies that if I start the problem from SEP for a vertical mass system, I can ignore the weight of the mass. Okay, so this is a ramification of what we are doing here, and I think this is best shown by means of an example problem. I'm going to do a very simple example problem, okay, so that our idea is more ingrained in our minds. Okay, so an example problem. Kind of a straightforward problem. In this problem, I have a link, okay, which is pin connected. Of course, I can't draw straight lines, which is pin connected at its end. Okay, let's see. I don't need that. Okay, so there is a pin support, and let's say that this link that I'm drawing is kind of massless, and I'll tell you what happens if we add a mass, or if the link is not massless, and so on. So let's say that this is a link, and at the end of the link I'm attaching a larger mass. Okay, so this is a mass which whose color I'll change in a second. Okay, so let's say that this is the mass M that is attached to the end of the link, and let's say the length of the link is capital L, and let's call this point as the point O. Okay, let's call this point as the point P. Okay, now obviously the system is not going to be in equilibrium because it's just going to plop down, right? It's like a simple pendulum. Now to put it in equilibrium, I do the following. Okay, so on the top side of the mass, I attach it to a damping element. Okay, I want to draw that as a straight line, of course, always. That did not come out as straight, so I'm just gonna get rid of that, copy that, and paste that and put that down here. Okay, that's better. So I'm not going to hazard drawing a straight line again. Okay, this end of this damping element is connected to the wall on the top here. Okay, and then on the bottom side is a spring. Okay, so spring is connected to the wall as well on the bottom side of the mass. Let's say that the damping element has a coefficient C and the spring has a stiffness K. Okay, so there is a mass, there is a damping element, and then there is a stiffness K. Okay, this is an example of a lumped mass model. Okay, so first of all, this is a massless bar. Okay, and there is a mass M connected here, and the idea is, okay, how do I obtain for small displacements? Of the mass from SEP due to an applied torque let's call that as M naught. Okay, so here is the applied torque. We need to obtain the equation of motion. Okay, Okay, so basic idea is mass m at the end of a massless bar of length L. Okay, applied couple moment. M naught on the system. As you can see, spring and mass sitting on. Okay, so from SEP, so what is equation of motion? Okay, so this is the basic problem. Once again, you got to recognize that, okay, this is a vertical mass system. Okay, it's a vertical mass because you see that the spring is going to get deflected by the weight of the mass m. Okay, so this is a vertical mass system. So notice this is a vertical mass system because the spring gets statically deflected due to the mass m even before any time varying motion takes place. Okay, so this is an important observation to make, which means that if I start this problem at SEP, okay, so which means we shall start this problem at SEP and we can then ignore the mg component due to reasons described earlier above. Okay, so that is the basic idea. So what do I have to do? Before I do anything, I have to do some kinematics. Okay, so I start off with some kinematics. What do I do here? I look at the degree of freedom of the system. So first things first, I take this figure and then I draw it out again. Okay, I know that it's a massless rod and so on, and so do you, so I'm not going to be worried about that at this point in time. Okay, and of course this is a torque that is applied. I'm not looking at that either. Length of this is known to be as L. Okay, so from the kinematics perspective, I know that the point O is a fixed point, so it does not have any acceleration and so on. So I'm just going to set up a coordinate frame. Okay, let's call this as the x-axis, the y-axis, and the z-axis with the corresponding unit vectors, little I, little j, and little k coming out of the page. Okay, so I know that acceleration of point O is 0. Okay, so we know now the degree of freedom is only the mass m. The number of configuration coordinates is going to be 2. There is going to be one constraint where the length of the bar is fixed, and so the degree of freedom is going to be only 1. Okay, so degree of freedom for the mass is going to be 1, and call this as theta. Okay, and the degree of freedom based upon the direction of the torque propeller, I'm just going to say, okay, this is the convention that I'm going to follow. Okay, if it goes this way, if it rotates counterclockwise, it's positive. If it rotates clockwise, it's going to be negative. Okay, so this is going to be theta of t. Okay, which means that this is also going to be the direction of theta dot and theta double dot. Okay, so if that is the case, then I can write the acceleration of the mass m, okay, which is acceleration of point P. Okay, so acceleration of the mass, okay, this is a particle along a circular trajectory, right? Which means that if I set up a coordinate frame and so on, so let me do that very quickly. I'm going to capture this and then bring it down here. Okay, so this is a circular motion for the mass. Even though I've drawn the mass to be pretty large, it is still going to be performing only circular motion, as you can realize. Okay, so I'm just going to call this direction as some e theta, and then this direction here is going to be er for me. Okay, so this is going to be er, and this is going to be e theta. Okay, so which means that from that perspective, the position vector for the mass, so if I call this as the point P, and O is the origin where I have my fixed frame set up, right? So this is my ijk coordinate frame which is set up here. So this is I, and then this is J. Okay, so the position vector of the point P relative to O is just going to be L times ER, and then if I differentiate this one time, R dot of P, which is the velocity of point P, which is the mass m. Okay, this is just going to be L theta dot in the e theta direction, and then the acceleration is just going to be, because the length is fixed, there is no time varying change from coming from the length. Okay, so this is just going to be minus L theta dot square ER and L theta double dot E theta. Okay, so these are the terms for the acceleration of the mass. Right, now we are assuming small motion. This is a very important statement. Okay, the ramification of that is the following. If I assume small motion, then it means that sine theta is approximately theta and cos theta is approximately 1. Okay, so small theta. And if that is the case, then here is what I can say. Okay, so if I bring my spring mass damper system down here, so if I copy that, then if I look at the spring, right, so this is theta of t, which is expressed here. Okay, so if the displacements are very small, then it means that if I look at the spring, so let me copy that spring, and let's say that I draw its free body diagram. Okay, so if I look at that spring, the displacement of the end of the spring is just going to be in the following direction. Okay, so this is just going to be a small amount L times theta. Okay, which means that the spring is going to be compressed by that particular amount. Okay, so the force acting on the spring is going to be a compressive force based upon the direction of the positive displacement that I have assumed. Okay, so this is going to be Fs, this is going to be Fs, and Fs is going to be K times L theta. Okay, that is the deflection of the spring. And if I look at the damping element, right, if I copy that and if I draw this out here, the bottom of the damping element is going to be having a velocity which is L times theta dot. Okay, the velocity of the other end is going to be 0. Okay, that is defined from the SEP. Okay, this is also defined from the SEP. Okay, so which means that if I look at the restoring force, okay, so this is going to be pulled down this way. Okay, this is going to be pulled down this way. Okay, so there is a force pushing on the spring, and there is something pushing back on the mass, and then there is a force of the damper that is pulling the damper down. Okay, so this is FD, and I call this as FD as well. Okay, so FD is going to be C times L theta dot. Okay, this is for very small angles theta. Okay, so that's very important to notice. Okay, so both of these are for small theta. Okay, so now I have the free body diagrams and so on. It is time for me to draw the free body diagram of the spring, and the damper is known to me. So free body diagram of the mass now. Okay, so draw the free body diagram and kinetic diagram of the mass. Okay, so what are the things? So if I look at this, I'm just going to copy that here. Okay, and then bring it down here. Okay, and once again, of course, copy that and bring it down. There are a couple of ways to do this problem. This is not just one way. This is just one particular way of doing this problem. Okay, so here is the mass m. Now the first thing I'm going to draw is the kinetic diagram. Okay, I have my ER and E theta direction, so I'm just going to grab them from here. And I'm assuming I have to maybe shift my drawings a little more. So this is the ER and the E theta direction, or let me just state this out here. Okay, so which means then I'm going to have a certain value here. Okay, let's bring this down here. Okay, so this is going to be m times AR. Okay, and then this is going to be m times A theta. Then what are the forces acting on the mass? There is, first of all, the mass is connected to this massless link or massless bar, which means there is a force acting along the length of the bar, so I'm going to call that as the tension T. Okay, then what else do I have? I have the weight. I don't have the weight because I'm starting from SEP, so I'm not including the weight. Okay, so that's a note that I want to make. So since we start from SEP for this vertical mass system, no need to include the term mg. Okay, so please do not do that. Please do not double count. Okay, so what are the only terms? The only terms are the following. Okay, so if I bring all of this a little down, and maybe I'll show the damping element and so on as well. So here is the damping element. I'm just going to copy that and bring it down here. I guess I want to bring all of them together at the same time. So shift this a little more. Bear with me, please. Take this guy and bring it right about here. Okay, that looks good. Then I'm going to say, okay, hey, if there is a force here, then there is an equal and opposite force back on the mass due to the damping element. Okay, this is the free body diagram. Not yet done, of course. We still have to add in the spring force, and I'm going to bring that right underneath. Okay, so here is the spring force. Copy that. There is no mention of the static deflection because that has already been taken care of. Okay, and then if I look at this, I'm going to have the spring force Fs equal and opposite to what I had drawn on the end that was connected to the mass. Okay, so those two are equal and opposite. This is the entire situation. I don't have the weight. Okay, so which means that and I can try reducing the size of these things, or maybe bring this down so that you can see all of them at the same time. Okay, so this is CL theta dot, and just cut that off. Okay, so this is the entire system. Okay, so this is the kinetic diagram of the mass, and here is the free body diagram. And it is obvious to see that in the free body diagram I am interested in looking at the equation of motion, which means I'm not interested in the constraint force. Okay, so if I do just these two, then I can say that if I sum forces in the theta direction, that is good enough for me. Okay, so since we are looking at equation of motion, sum of forces in the theta direction on the, this is the free body diagram, and this is the kinetic diagram. Theta pointing down to be positive. This is equal to sum of forces in the theta direction on the kinetic diagram. Theta direction positive down. Okay, what are the forces? I'm going to have minus Fs minus Fd, and then there is also the torque that I have applied on it. So in a sense you can think of it as I guess in a massless sense. Let's say that instead of the torque there is a force acting, because I'm just treating this as a particle, right? So from that perspective, let's say that there is a force acting. Okay, I apologize for that. That was not my intention. I wanted to actually give this rod a particular mass, so let me cut that off, and then let's say that there is a force acting. Okay, we will look at how the torque can be taken into account as well. So this is the force acting, let's say F of t. I'm going to look at the torque as well, so don't worry about that. Let's say that there is a force F of t which is acting vertically down. This is the applied force. Okay, now if I look at it as f of t, then there's going to be plus f of t, and this is just going to be equal to m times a theta. If I just start doing the substitutions, this is minus k l theta cl theta dot, and then f of t is equal to m times l times theta double dot. Okay, so that I can start doing the calculations and the substitutions and so on. Okay, once I do that, I'm going to have ml theta double dot cl theta dot kl theta is equal to f of t, or I can say this is m theta double dot c theta dot k theta is equal to f of t by l, or if I want to write it in the standard form, I can divide through by the stiffness, and I can say this is m by k theta dot c by k theta double dot c by k theta dot, and then k by k theta is equal to f of t by l times k. Okay, and this is the point where we will start writing the damping ratio and so on. Okay, so once that can be done, we can write this in the standard form as 1 by omega n square theta double dot plus, this is going to be 2 zeta by omega n theta dot, and this is just going to be theta is equal to f of t by l times k. Okay, and here we can define omega n square is equal to k by m, and zeta is equal to c by 2m omega n. Okay, now the obvious question is, okay, what happens if there is a torque applied? Okay, so here is the basic idea. Let me go back to my problem. Let me grab my problem and come back here. I wanted to first show it as a force applied and then as a torque applied. I kind of overthought myself and then put the torque directly on there. So what if there is a torque applied instead of the force? Now, one thing to consider is that if there is a torque applied, then is the bar going to be massless, or is there going to be a certain mass to the particular bar? Okay, you can consider both the situations. I'll talk about the other situation later, but here could be one way of thinking about it. So instead of the force applied, okay, I can think of it as a torque that is applied on this system, which is going to cause it to deflect by the amount theta from SEP. So this is m naught, okay, and this is deflecting by the amount theta from SEP. Okay, so I call this as SEP, and this is theta of t. That is the deflection that is caused. Here is what you can do. You can draw the entire system, okay, as a free body diagram. Instead of drawing just the mass, let me grab my figure from above. Okay, all this system of things that I have already drawn, I will need them. Okay, I'll bring this entire situation and then show this down here. May not have enough space to do it, but let me bring it to the next page. Okay, hang on. Okay, now I will not be showing any of these. This one I'm going to bring it on to the side here. Okay, rather than show the tension now, here is what I'm going to show. And of course there is this force Fs which is acting here as well, so just make sure that you have that on there. So this is the force Fs which you have already taken into account. Now I'll show this guy here. Copy that and then bring that down here. Okay, and move this guy and then bring that down here as well. Now you see, of course this is not going to be shown on the kinetic diagram, right, because that's an applied torque. Now on the free body diagram, here is what I'm going to show. Because there was a point that was pinned here, right, there's going to be a pin reaction, OX and then OY. Okay, then the idea is, okay, how do I find the equation of motion? Now you see I can't just sum forces up, right, because that's not going to help me. So I'm going to call this point as O, this is the total length L, this is the total length L. Now to find the equation of motion, because I have the pin reactions, here is what I have to do. Find the equation of motion if we consider a torque acting on the system, okay, rather than an applied force. This is an applied torque. Okay, I can't sum the forces up. I have to apply the sum of moments about the point O. I can say the following: sum of moments about the point O on the free body diagram should be equal to sum of moments about the point O on the kinetic diagram. Just say that, okay, clockwise torques are positive, and if I look at that, it is fairly straightforward now, right? So let me bring this entire setup down and start summing moments up and going crazy after that. Okay, so this is the situation. What are my moments? I'm going to have first of all the applied torque, so that's m naught. Then I'm going to have fd times length L, but that's going to be in the clockwise direction. Then fs times length L is going to be in the clockwise direction. Now I don't have the force F of t, I have the torque that is applied here. I just want to make a note of it. Okay, here, okay, so what happens if we have a torque m naught acting on the bar rather than a force F of t on the mass. Right, so this is the basic question that we are going to be answering. Okay, and here is the torque that is acting. So this is a system once again taken from SEP. Okay, so from SEP, okay, this is still a vertical mass system. Okay, Fs and Fd remain the same as before. As before, the acceleration of the mass is also going to be the same as before. Okay, so acceleration of the mass is still going to be minus L theta dot square ER L theta double dot E theta. This is also as before. The only difference is that when I'm drawing the free body diagram, now I have to draw the entirety of the situation where I show also the pin reactions OX and OY. Okay, and then as you can see, this is fairly a routine procedure. I'm just applying moments about the point O so that OX and OY do not become a part of my equation of motion. And if I now look at the other side, this is going to be m times a theta times the distance of L. Okay, so this is now going to be the following. So m naught minus k times L theta times L theta dot times L. This is equal to m times L times theta double dot times L. I should be getting the same properties of the system. The natural frequency and the damping ratio should not be different just because I'm applying an applied moment. Okay, they should be the same as before, and you obviously see they are the same as before. If I rearrange the terms, this is ml square theta double dot cl square theta dot kl square theta is equal to m naught, which is the applied moment, or if I multiply divide through by L square and divide through by K theta double dot, then I'm going to have CL square by KL square theta dot KL square by KL square, of course, theta. That's going to be m naught by KL square, or I can write this in a standard form. The L square cancel off, and all of this cancels off here. Okay, then you write it in the standard form. M by K is 1 by omega n square, so this is 1 by omega n square theta double dot. And then I'm going to have this as 2 times zeta times omega n theta dot, and then this is just going to be theta and m naught by KL square. Okay, so this is going to be the equation of motion. Okay, and in this case the natural frequency is still the same, and zeta is still the same, c by 2m omega n, same as the case where f of t acts on the mass, because these are properties of the system. These are not dependent on the applied forces. Okay, so which tells you that omega n and zeta are properties of the system and are not dependent on the applied loads. Okay, so this is the basic idea, and just to give you a very quick recap of what we were doing, this is an important idea in my opinion. Okay, so here is a quick recap. If I go back to the main figure, I start off with just a spring. Okay, the spring is sitting there minding its own business, doing nothing. Then I gently come and place a mass right underneath the spring. I don't apply a force on this mass, I don't apply any initial displacements and so on. So at this point in time, the system has to be in static equilibrium. This is static equilibrium. Okay, as you can very well imagine. And if it is in static equilibrium, it means that the spring has been deflected by an amount delta static due to the weight of the mass. Okay, this is due to the weight of the mass. Okay, and in static equilibrium, all the forces have to be balanced, so K times delta static is equal to mg. Now if I had a damper attached to the same thing, what would happen? Nothing would happen, because the damper would not be feeling a restoring force to a displacement. Dampers always react only to a velocity or a relative velocity. Okay, so there would still be no change in my situation at all, whether I had a damping element attached or not. Okay, which is why I did not show a damping element, and you will see that in the example that I'm showing down below, it doesn't make a huge difference either. Then I say, okay, hey, from the SEP, deflect the mass by an amount x of t. What's going to happen? Then the mass is going to start showing oscillatory behavior due to the applied force f of t. Okay, there is a force applied, f of t. And if I now draw the free body and the kinetic diagram from the SEP as the mass is getting deflected, here is the situation that I have. Okay, so these are all things that I see, and maybe I want to scoot this down a little onto the side so that you can see everything. I guess you can see x dot and x double dot here, right? Okay, so let me just slide that down onto the side. Okay, so that is the positive sign convention for x dot, x double dot, and x of t. Okay, what are the forces acting on the mass? The applied force f of t, the spring restoring force, and the mass mg, the weight of the mass mg. Okay, on the kinetic diagram, I'm going to have mx double dot. If I do the sum of forces, then I end up getting the following. The standard form of the equation shows that there is no presence of mg at all here, and so we come to an important conclusion that when a mass moves in a vertical direction, if I am measuring the position of the mass from SEP, then the weight of the mass is not going to play a role in the problem. Okay, if the deflection of the mass is measured from SEP. So if I start the problem from SEP for a vertical mass system, I can ignore the weight of the mass. This was the big takeaway. Okay, so big claim of the day in a sense. Okay, so this is the big claim of the day, and we had just proved that earlier. Okay, and I just exercise this for a problem. I have this system set up here. I have a mass m, I have an applied force. I had initially considered a torque, but then I thought better of it and said, okay, let me first look at what happens if I apply a force on the mass. Then let's say that, okay, hey, rather than applying a force, how about I apply a torque on the system? What's going to happen? The equation of motion in the fundamental form should not be different, because the natural frequency and the damping ratio are still going to be the same for the body. Okay, it's a property of the system. It's not a property of the applied force or the applied couple moment. Once I do this, I say, okay, we are measuring it from small deflections perspective. So sine theta is theta, and then cos theta is 1. Okay, and once again, I'm looking at it from an SEP position. It's a vertically deflected system, which means that I'm not going to be including the term mg. And I typically look at the degree of freedom as theta here, which you have seen in many problems earlier. Okay, so we don't need to go over it again. I look at the acceleration of the mass, derived from first principles. Once I do that, then all I have to do is look at the free body diagram of the spring and the damping element. Okay, so these are all free body diagram of the springs, free body diagram of the damping element. Okay, why am I not drawing the kinetic diagram for these? This is because they are considered to be massless. Okay, and this is for small theta. And then I combine them all together by drawing the free body and kinetic diagram of the mass as well. Sum of forces gives me the equation of motion written in the standard form. This is the natural frequency. Okay, omega n, and this is the damping ratio, zeta. Okay, these are properties of the system. Okay, they do not depend upon the applied forces. You can apply any kind of a force or as many forces as you want. That should not change the value of these parameters. Okay, and that's exactly what we proved. We said, okay, so what now if we have a torque acting? What's going to change? Nothing much is going to change. The equation of motion is going to remain similar in its fundamental form, except that I'm just going to apply sum of moments at a certain point rather than applying sum of forces, which is exactly what we did. We came up with the standard form of the equation of motion. It did not change by a whole lot except for the term on the right hand side, which is called as the forcing term. Okay, so these terms are called as the forcing terms. Okay, and likewise you can also say the same thing of this equation of motion as well. This is also called as the forcing term because it forces the system to dance to its tunes. That's why it's called as a forcing term. Okay, and once we have this, then we are good to go. We can solve this equation of motion for given values of the parameters and try to understand the behavior of the system. All right, I hope this lecture was useful to all of you. Take care of yourselves, and I will see you in the next lecture. Okay, bye bye.